One thing we have to think about in chemistry is the phase of matter. If you want some water, you're probably going to go get a glass of water. You probably wouldn't go get a piece of ice to try and suck on, although that would work, although it's just a little bit more awkward. And I definitely don't think you would take water vapor, i.e. gaseous water, and try and use that. You'd want the liquid water. So knowing what phase you have is really important. Now, in the planet Earth, there are three main phases that are important, and they're called solid, liquid, and gas. And a solid, like the ice cube, has very rigid space with fixed volume. So it's very structured. You can throw it at each other, blah, 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 and stuff like that's cool. Now, liquid water, which is probably what you want to drink then, flows. It doesn't have a fixed shape. It does have a connection, one molecule to the other, but it's a lot different. It takes on the shape of the container. If you put a piece of ice in a glass, it stays the piece of ice, but liquid will kind of merge and figure out what kind of container you have. So there's definitely differences between those. And gases just expand to fill the shape and volume of the container. They don't have fixed shapes or volumes. They're very, very flexible. So gases, liquids, and solids, we'll talk about all of those in this class. However, in the universe, the most common phase of matter is referred to as plasma. And plasma, which is kind of rare on the Earth, is very, very common outside of the Earth. So for example, the sun is basically a big source of plasma. We do see plasma on the Earth in the form of lightning and stuff like that. But anyway, plasma is basically gaseous matter that's electrically charged, and it's a whole nother ballgame. We'll talk about that more next term in Chemistry 222, but for right now at least, just kind of keep that in the back of your mind. So again, here's water as a vapor, as a solid, and a liquid. You can see the differences. And again, if you want something to drink, you're probably going to want the liquid version and not ice or, for example, gaseous water. But it's not just water. There's bromine in the upper right-hand corner. Bromine can be a solid. It can be turned into a liquid pretty readily. It's kind of a nasty, dark brown, red kind of thing. And the gas is also relevant, and you can see it. It's kind of a reddish haze and stuff above the bromine. It's a lot more dangerous to deal with than water, but it is something that chemists deal with, and if you're safe, you can deal with it too.
According to the kinetic molecular theory, the molecules of a solid are locked in place, though they have motion. Molecules of a liquid are closely associated with each other, but move relative to one another. Molecules of a gas move independently and occupy a much larger volume than those of a corresponding liquid or solid.
So in chemistry, we use something called the kinetic molecular theory to talk about how the different phases are different from each other. And KMT, which we'll abbreviate KMT a lot for kinetic molecular theory, is the theory that's used. And you can see from the pictures, their solids are very, very tight together, all right? They have not a lot of room between the molecules, and they all move together as one. Liquids, there is a connection between them, but it's more loose, if you will. It's more flexible. So that's why liquids will fill the container you pour them into, but the liquids don't kind of go off on their own either. Gases, on the other hand, have no control over each other. They're very independent molecules. They'll take up and fill whatever volume you set them to. And of course, they will also float away if you're not paying attention and stuff, which is something to remember. One consideration that chemists and also material scientists and stuff like that need to think about is the energy required to turn solids into liquids or liquids into gas. And vice versa, sometimes it's nice to think about the energy required to turn gases into liquids and liquids into solids. And this is something we will talk about this quarter definitely. But two terms I'm going to use here to describe these processes are endothermic and exothermic. Now, an endothermic reaction takes energy. You need energy to make that happen. And anytime you go solid to liquid or liquid to gas, it's an endothermic reaction. So having a solid go to a liquid won't happen unless you add energy to it. Same for liquid to gas. On the other hand, the opposite processes are exothermic. They release energy and stuff when they happen. So when you have, for example, a gas going to a liquid, energy is actually released. And going from a liquid to a solid, energy is released as well. Now, usually endothermic reactions, if you have an endothermic reaction happen, it takes energy, so your container will feel cold because usually it absorbs energy from the outside to make the inside reaction happen. So the container itself ends up feeling kind of cold. Likewise, an exothermic reaction, usually the reaction then, the container feels hot because energy is released in the process. So all of your fireworks, making water, as I talked about earlier, all those kind of things, those are exothermic. Energy is released. You can maybe see it. You can feel it if you feel the container, stuff like that. On the other hand, if you've ever used a cold pack, like after a sports injury, those feel cold, which is intentional. Those take energy to happen, so those are considered endothermic. And we will talk more about this later, but this is one of the considerations that chemists must use in order to make that happen. Now, in the middle lower picture right there are different terms that are used to represent this. So a solid going to a liquid, there's an arrow pointing up, that's melting process. So if you melt something, that's a solid going to a liquid. On the other hand, a liquid freezing, going back into a solid, oops, I gave it away there. A liquid going back into a solid, that's freezing, all right? And so these are just terms that we'll introduce later on. So liquids going to gas, you vaporize them, or it's vaporization. On the other hand, if you want your gas to go back to a liquid, that's condensation. And finally, you can have a solid go directly to a gas and a gas go directly to a solid. Now, a solid going to a gas is something you may have seen if you've ever used dry ice, which is carbon dioxide. Carbon dioxide goes straight from a solid to a gas. It sublimes, or it's the sublimation process. It is possible to take the CO2 and condense it back into a solid. That's called deposition. And we'll talk about these terms more later, but the most important thing here is if I talk about endothermic or exothermic, endothermic, it takes energy and the container would feel cold. On the other hand, exothermic releases energy and the container will feel hot. To understand science, we have to talk about different kinds of measurements that we're going to take. And the most important one probably is mass. And mass is very important in chemistry. Now, mass and weight get mixed up a lot. And in chemistry, we usually don't make a big deal of it. But I want to talk about the official rules of how this all works. Mass is literally a measure of the matter in an object. So if you make a measurement in grams, kilograms, micrograms, nanograms, etc., that's the mass. It talks about how much mass is inside the object, which is great. Weight, which is what a lot of times people confuse with mass, is officially a force that gravity exerts on an object. And weight and mass can be different, all right? When you measure, if you've ever measured yourself in pounds, like on a scale, that's technically the weight. And that has to do with gravity. And the reason why scientists don't usually like using weight is that weight can be different if you're on a different planet or on the moon or something like that. So your weight is different on the Earth than it is in Mars. So you can see up there in the picture in the upper right-hand corner, there's a person with a mass of 50 kilograms, and on the Earth, that would be a weight of about 110 pounds. But on Mars, the weight would be only 42 pounds. However, notice that the mass is the same. So chemists usually use mass in grams and kilograms, stuff like that. We don't usually use weight. And of course, in space, where you don't have any gravity, usually it would be totally messed up. But again, the mass would be the same. So that's why chemists use mass whenever possible. There's something called the law of conservation of matter, which I'll sometimes abbreviate the law of mass action, that just says that mass can't be created or destroyed. And it's very helpful when you balance a chemical reaction, when you want to know what one chemical turns into later. And we'll talk about this more later. So just realize that officially you should use mass for measurements when it comes to things. Don't use weight, all right? If you call it weight, and even I might call it weight by once in a while, which is fine, just realize that technically we should all be using mass for measurements and not weight. By the way, weight is often done also in newtons, which is a type of unit, as well as pounds. But again, we're going to try and steer clear of those and just use grams, kilograms, nanograms, stuff like that.